Hi everyone, welcome to the Machine Learning Meetup. I'm Martin Goodson from Evolution AI, who are the sponsors of the meetup. I'm joined by my colleagues Alexey and Giuseppe, also from Evolution AI. And today our speaker is Alexey Bochkovskiy from Intel, who will be talking to us all about object detection. So as usual, Alexey will talk to us for about 40 minutes, and then we'll have 20 minutes of Q&A. And today our Q&A will be moderated by Sasha Sachs, who's a PhD student at UC Berkeley. As usual, please add your questions into the QA function. So not the chat function of Zoom, but the QA function. And also put your hand up at the same time if you would like to ask your question live. Otherwise, Sasha will just read out your question. But if you want to speak live, then put your hand up. We prefer people to ask their own questions, so do put your hand up if you can. And with that, I'm going to hand over directly to Alexey.
Hi everyone, my name is Alexey Bochkovskiy, and let's start. And I want to talk about YOLOv4 and DPT, that's prediction transformers, and neural networks for different computer vision tasks. There are at least 4 computer vision tasks like classification, object detection, depth estimation, and semantic segmentation. And as you can see at the top left image, there is classification task, and the correct answer is wooden spoon, but it's not obvious that this is the main object that we need to predict this. That's why the most of users usually use other tasks for their real-life tasks, like object detection or semantic segmentation, when we need to predict different objects with different scales at different positions. And there is another one task, depth estimation, when we need to predict distance from camera to the object for each pixel. And there are at least 2 different tasks, stereo depth estimation and mono depth estimation. Mono depth estimations means that we use only one input image. And in this case, our neural network just need to remember to know 3D shapes of all objects. So why we should talk about YOLOv4 rather than other networks for object detection? There is a chart from Papers with Code site for object detection task on Microsoft Cocoa dataset. And vertical axis is an accuracy, the horizontal axis is a date, and the green line is the highest accuracy of the net neural network at that time. And the red line is the history of accuracy of different YOLO models: YOLOv3, YOLOv4, scaled YOLOv4, and YOLO-R. Blue line is the accuracy of YOLOv5 models. There are at least 6 different YOLOv5 models. And as we can see, scaled YOLOv4 was the most accurate neural network at release time. And at the same time, it was the best in terms of speed and accuracy in the very wide range. And currently, the most accurate real-time neural network with 30 FPS or higher is YOLO-R neural network. It is scaled YOLOv4 based neural network. But also, it's much more important to understand the speed of neural network and ratio of accuracy and speed. There are 2 charts with accuracy and latency. The left chart is for WIMO real-time to detection dataset. And as we can see, YOLO-R, that is scaled YOLOv4 based, is the fastest neural network and the optimal neural network in terms of speed and accuracy. It is more accurate than YOLOv5 by 5.4%, and just slightly less accurate than DD-Map Vision or Leap Motor Det, but much faster. That's why it's more useful. And the right chart is the accuracy latency chart on Microsoft Cocoa dataset. And as we can see, there are three the best and the most accurate real-time neural networks: Scaled YOLOv4, YOLOr, and new YOLOr that was released recently. And as we can see, they are much better than many other computer vision object detection models like YOLOx, YOLOv5, PP YOLO version 2, or even better than transformer-based neural network like mask RCNN with swing base and deformable data. And another one question, why we should take the DPT model as an example. There is a chart from papers with code with a vertical axis RMSE error, the lower the better, and the horizontal axis is the date. And as we can see, DPT hybrid has the lowest error among all other neural networks. But much more important, the bottom table, there we show zero shot error. So the lower the better, and we train it on one data set, but we test it on other data sets from different domains. And DPT much better, much more accurate than all previous neural networks for molecular depth estimation. So, and we used convolutional neural networks for YOLOv4 for object detection, but we used transformers for dense prediction tasks, depth estimation, and semantic segmentation. But why did we use different ways, different neural networks for these different tasks? There is an answer, because transformers, VIT, Bayes, Swin, they are better for dense predictions with low resolution, because transformers are better for small network resolution, or maybe we can use it for high resolution, but we will have very low speed. So yes, we can use it for high resolution, but if you don't need high speed. Transformers are better for large data sets, or if you have many data sets, like for depth estimation, we use MIDAS training pipeline, where we can combine many different data sets which are collected from lidars, radars, synthetic data, stereo films, and so on. And another one thing, transformers are better when we use accuracy per pixel, because transformers are better for large objects. Large objects cover a larger part of image and affect on more pixels. That's why we can get high accuracy per pixel if you predict large objects very well. While convolutions are better for object detection with high resolution, and if you need high speed. Another thing, convolutions are better if you have small data sets, and if we need to use accuracy per object. So we need to predict small objects and medium and large objects, and it doesn't make sense. So we don't prefer large objects rather than small objects. That's why we use it YOLOr and for YOLOr and Scaled YOLOv4 we used convolutional neural networks, while for depth estimation and semantic segmentation we use it transformers, exactly VIT, and we achieve very high speed and high accuracy in both tasks. For depth estimation and semantic segmentation we used low resolution, about 400 pixels, while for object detection we used high resolution, 1280 pixels. There is the scheme of Scaled YOLOv4 neural network. There are a series of 3 networks, P5, P6, P7, which have different number of layers, of downsampling layers, and different number of outputs. Detection P3 for small objects, and detection P5 for large objects. But the most important thing, the most important part, is top left block, CSP block, cross-stage particle connection. When we just get layers between two downsampling layers and divide number of channels twice. And then we add residual connection, but not as usually. We use concatenation instead of adding, and we add additional convolutional layer for this residual connection, and we call it CSP. And in this case, this neural network can achieve the same accuracy, but twice, but it will be twice smaller, twice faster. And if we want to improve accuracy, then we can just increase number of channels twice in the whole network, and it will have the same speed as initial model, but it will be more accurate. And we use this block in all our networks, in all our convolutional networks. There is a scheme of DPT, dense prediction transformers. We use VIT as a backbone, vision transformer, but there is a question how to use features from VIT and how to upsample them to the initial resolution. So there are many different ways. We can get just features from the last layer or from intermediate layers. We get features from different layers. For example, if you have 12 layers in VIT, then we use features from layer 3, 6, 9, and 12. And then we use the convolutional layer for upsample. And we use just FPN feature pyramid network up to VIT, and then just fuse these features from different layers and upsample it to the initial resolution. So what is the difference between convolutions and transformers? There are advantages and disadvantages of transformers. Advantages: global receptive field, because each actuation at each layer in VIT sees the whole image, while in convolutional networks, convolutional layer sees usually only 3 by 3 pixels from the previous layer. So if you need to increase receptive field, we need to stack many different many convolutional layers. So for example, the first will see just 3 by 3, the second 5 by 5, the third 7 by 7, and so on. And then we need to use downsampling layers to increase it twice. And the second advantage is attention. Attention blocks unnecessary signals during inference and training, so it doesn't spoil weights if features they generate are not currently required. And there are two disadvantages of transformers. The first is related to global receptive field. So due to this self-attention mechanism, we have quadratic dependence on network resolution. And it's very low for high resolution. For example, if we use 400 pixels resolution, then it works well. But if we use 1000 pixels, like in object detection task, then it works very slow, and I will show this. And another disadvantage is there is no default shift invariance in VIT. So if we change position of objects, then it will generate different signals. So we need to train VIT longer to learn this shift invariance. And another, what does it mean? Why VIT works better for large objects and why convolutional networks work better for small objects? VIT works better for large objects because it has global receptive field. So even the first layer in VIT sees the whole image, and it covers the whole image and it sees large objects. And at this table, we see accuracy for object detection for two different models, VITB16, Transformer-based, and REST-on-net, convolutional neural network. And we see that VIT is much better for large objects by 4 relative %, while REST-on-net has the same accuracy as VIT for small objects, while it's 3 times faster. So if you will try to make REST-on-net convolutional network with the same speed, with the same size as VIT, then REST-on-net will have better accuracy for small objects, and VIT will have better accuracy for large objects. Another difference is from DPT paper, from our paper. We tried to train two networks, convolutional and VIT, with low resolution, 400 pixels. And then we tried to increase this resolution up to 600 pixels and test accuracy. And we saw a drop in accuracy, but accuracy for convolutional networks drops much more than for VIT. And we assume that this is due to a global receptive field in VIT. So when we increase the resolution, in VIT, we don't need to add some new layers because our VIT already sees the whole image. While for convolutional network, if we increase resolution, we need to increase depth. We need to add more layers, more convolutional layers with 3 by 3 kernel size to cover the input image. And this is explained very well in EfficientNet paper. So if you want to scale up some network, we cannot just increase resolution or increase depth. We need to increase both resolution and increase depth to cover this resolution, to increase receptive field. And what is the difference between computational complexity between convolutional and transformers? For example, computational complexity of convolutions depends on resolution linearly, while for transformers, we have quadratic dependence. So why does it happen? At this scheme, our part is for convolutional neural network, for convolutional layer, and usually we can perform convolutional by using two ways. The first way, just in a loop, apply these kernels and do it as usual. But there is another one way, by using general matrix multiplication. And to do this, we need to change our input by using into-call function. It uses sliding window, and then we get changed input, to which we can apply general matrix multiplication and use unchanged weights, and we will get output the same as for convolutional layer. And in this case, we see that this general matrix multiplication depends on resolution linearly. And bottom part of this scheme is for self-attention in transformers like VIT and SWIN. And in this case, we see that query and K, they both depend on resolution. And in total, we have quadratic dependence of computational complexity on resolution. And it means that if we have some small neural network for image classification task, for example, for ImageNet with resolution 384, and it works well, it works fast with high accuracy, it's great. But if we will try to apply this network for object detection with 1000 pixels, and if we will try to increase resolution on network, then we will have very slow speed of VIT or SWIN. And at the middle of this slide, I show two neural networks, dual SWIN base and YOLOv4. They both have approximately the same accuracy. SWIN just 1% more accurate, but YOLOv4 is 16 times faster. So SWIN is very slow, and SWIN doesn't solve this problem completely. But SWIN tries to solve this issue, at least partially. They apply attention not to the whole feature map, but they divide feature map by windows and apply self-attention only inside window. But if we use some small SWIN with low resolution, and if we want to try to use it for high resolution, we have at least two ways. We can increase number of windows, and in this case, we will have linear dependence on computation complexity on resolution, but actually we will have quite low accuracy. Another way try to increase windows to keep the same number of windows, but increase size of window. And in this case, we still have quadratic dependence, and it's still slow, as I showed it previously. But there is some solution. It is perceiver. When we use just trainable parameters for query, it is fixed trainable parameters with fixed size. And in this case, we use such cross attention block at the first layer with these trainable parameters. And as a result, we have output with fixed size. And then for all other layers, we use this these fixed size tensors. And in this case, this part of network doesn't depend on resolution at all. So we solve this issue. And it seems this works well. So they tested perceiver on many different computer vision tasks, like image, video, text, audio, and reinforcement learning, like Alpha Star for playing startup game. And it works well. So why attention mechanism helps in VIT? Attention blocks unnecessary signals. So for example, on this image is for depth estimation. Left column is input image, and then we see MIDAS, convolutional neural network, and then DPT hybrid. This is hybrid convolutions with VIT, and DPT large, just VIT. And as we can see, for convolutional neural networks, we have some large false detections, false predictions. And these false predictions are wrong, and they just overlaps with some small details and generates large error. While for DPT large, we don't have such false predictions. And for DPT hybrid, we don't have such false predictions. And also we have some more fine-grained details. So it seems that DPT hybrid, when we use both ResNet 50 plus VIT, such hybrid model, and it seems it works better for small objects. But how does attention work, and why does it help? For example, let's look how does gradient descent work without attention, just for very simple convolutional with kernel size 3×1 without bias. So we have, for example, 3 inputs, 3 weights, and we get out. And during training, we use break propagation, we get gradient, and we calculate deltas for weights. We multiply gradient by corresponding input. And if you have some batch with batch size 3 with 2 samples, 1 and 3, and positive samples and negative sample 2, then we do the same. And as we can see, weights try to be like inputs with the same shape for positive samples and inverted for negative sample. And after averaging across samples in batch, we have some averaged weights. And the resultant weights generate high positive output for samples, for positive samples 1 and 3. And it generates a low positive value or negative value for negative sample, sample 2. This is what do we want. But how does gradient descent work with attention? So attention was used not only in VIT, in transformers, it was used in many different networks, even in convolutional networks like squeeze and excitation block, in efficient net, and SqueezeNet, and so on. And the simplest implementation of attention is just additional one branch. And for this branch, we apply sigmoid logistic activation or softmax. And then we do element-wise multiplication between main branch and attention branch. And how does it work and how does it help? during inference, it helps. So if attention is 1, then it doesn't do anything. But if attention is 0, it blocks unnecessary activation. So it helps to avoid some unnecessary predictions. While during training for propagation, if attention is 1, it doesn't do anything. But if attention is 0, then it blocks gradient. So in this case, it doesn't spoil the weights. So if this feature is not necessary, attention blocks this feature and block gradients. So this gradient will not spoil the weights. In this case, we can use neural network with attention has high capacity because unnecessary signals doesn't span this capacity. Another one, disadvantages of VIT, of transformers, there is no default shift invariance in VIT. So there is scheme. Left part is for VIT, right part is for convolutional network. And for example, we have convolutional layer, convolutional network with stride 16. And if we have some object, and if we shift this object by 16 pixels, then this network will generate the same signal, but from shifted output. But the signal will be shifted in the output, but it will be the same value. While in VIT, even if we use VIT B16 with stride 16, and if you will try to move object by 16 pixels, it will generate output in different output, but also it will generate different output value, because there will be applied another one position embedding, and even input already will be different. And in this case, we need to learn. We need to train VIT, so it should be learned during longer training. This shift invariant should be learned, and that's why it requires longer training, because it doesn't have inductive bias. And overall, so due to the trainable attention mechanism, and as a consequence, the trainable receptive field. So in VIT, receptive field can be trained and can be local or global. And in this case, transformers are more suitable for various types of different tasks, like text, audio, image, video, and reinforcement learning. And due to this, we also can try to use multimodal tasks when we just make one neural network that can solve many different tasks simultaneously, like CLIP, GLIP, Florence, WET, and different neural networks. In this case, attention approach helps to switch communication between different tasks or disable communication between different tasks when it is not necessary. And it helps a lot, while many convolutional networks like ResNet, ResNext, they don't use attention approach. And they has a small local receptive field, and it cannot be global. But what about fast transformer-based networks? Previously, we saw that, yes, YOLO is much faster, 16 times faster than SWIN, DOL-SWIN for object detection. But maybe at least for ImageNet, we have some very fast transformer-based networks. And yes, we have, for example, Levit. Levit is a hybrid model. There are used some approaches from convolutional networks and from transformers networks. And this is chart from Twitter from Ross Whitman, maintainer of PyTorch image models. There are more than 500 points of different models, convolutionals and transformer-based. And it seems that Levit is the optimal neural network in terms of speed and accuracy, at least for ImageNet. And it seems that it's a very promising approach, at least for low resolution. And there is still issue how to apply it for high resolution. And currently it is not solved task, but it's very promising. And there is another one, Selflimit vision transformer, and they stated that it's even better, more optimal internal speed and accuracy than Levitt. And let's try to talk about other problems and ways to solve different computer vision tasks. For example, there is some problem, some issue. As I showed it previously, VIT doesn't have shift invariance, while convolutional network has shift invariance by design, by default. But it would be great if some neural network will have both shift, scale, rotational, and maybe elastic invariance. So for example, if we train some neural network with just object at one position, at one scale, and at one angle, and then we change shift, we shift this object, or we change scale, and then neural network will predict such object without data augmentation, and it will be great. It will much better. It will have much higher capacity. And the second issue, when we train, for example, object detection, we usually use different formulas, different algorithms for training and for evaluation. For example, training loss and validation accuracy mismatch. So we train detector with RMSE loss, but we evaluate detector with average precision accuracy. So teach one thing, but demand something completely different. And moreover, in real life task, we even want something different than AP accuracy. And one of the solution, what was used in YOLOv4 and scaled YOLOv4, is IOU loss, intersection over union loss. So instead of RMSE loss for bounded box regression, we used IOU, and it helps a lot. It increases average precision significantly. And another one way, try to make differentiable detector head or some option of non-maximum suppression. And there are some papers, they try to make such non-maximum suppression that can be differentiable. The third issue is lack of 3D data augmentation. So currently we use data augmentation, but we use it in the observation plane. So we just use shift, rotation, and rescale. But we don't use perspective transformation. In this case, if we have, for example, several photos, several images of the same environment, we can try to use NURF, 3D reconstruction, and we can rotate this environment in 3D space. Or for example, we can try to use just one image and do the same by using 3D photo in painting. This is very interesting thing. So we just use MIDAS or DPT. We predict depth of the image, and we reconstruct this image, and we can rotate it in 3D. And we can generate label. If we have label for initial image, we can generate labels for rotated images. And in this case, we can try to use such data augmentation and try to train using this approach, and it can help. The fourth problem is lack of simulators for synthetic data. And we try to use a lot of synthetic data for DPT, for dense prediction. So we used some simulators, some 3D engine, and we see that even images and labels from simulators, synthetic data, helps a lot for real data. So when we add synthetic data, then we test on real images, and our DPT model can predict depth much better. So this is one of the way how to improve at least depth estimation, monocular depth estimation. And the fifth issue is lack of approaches for fully automatic collection of ground truths. It's very strange. So there is a question, how can we collect labels automatically? There is no such device which can create bounded boxes for objects or for semantic segmentations, some labels. But there is at least one task where we can collect labeled dataset, labeled training dataset automatically. This is a depth estimation. We can use RGB camera and LiDAR or stereo camera or radar, and we can install it on car. This car can drive, and it will collect images and labels automatically. Depth is label. And in this case, we can collect very large training data set, and we can create VIT model, very large VIT model like GPT-3, and we can train such large VIT model with such large data set, and it will predict very great depth. And which neural network will be preferred in the future? So, for example, let's look at these two neural networks, YOLOv4 CSP and efficient DAT-B3. They have the same accuracy, but efficient DAT has 2.4 times fewer flops, but at the same time, it is 2 times slower. So it's very strange. Efficient DAT has lower flops, but lower speed. And there is an issue because there is imbalance between computational complexity and memory speed requirements. So in efficient DAT uses depth-wise convolutions, which has low computational complexity but high consumptions in memory bandwidth. That's why even if we decrease number of flops, if we reduce computational complexity, it doesn't speed up this network because memory bandwidth is a performance bottleneck. And the second thing, high degree of parallelism. This is a very important thing. So if we just use many layers, very deep network, and these layers should be performed sequentially. So it cannot be parallelism. While much better if you use fewer layers, but much wider layers, like in VIT, and it can occupy GPU much better. And so for the future hardware, we need to create such neural networks which can be very well parallelized, and which can be performed on multi-chip GPUs. For example, there is Intel Ponte GPU that consists of 47 chips. And that's all. Thank you for your attention.
Thanks so much, Alexey, for the fantastic talk. Now comes the QA section. We're going to be moderated by Sasha. So people in the audience, please do add your questions to the QA function. But I'm going to hand over to Sasha. Oh, I should just remind you, if you want to ask your question live, then also put your hand up at the same time that you put your questions to QA. Okay, over to Sasha.
Sorry, I don't hear you.
Are you on mute, Sasha? Maybe Sasha is on mute. Maybe I can ask a question while Sasha is processing his microphone up. So I was just going to ask you, you mentioned a couple of times, Alexey, about the computational constraints or kind of complexity of the transformer-based approaches. Do you know if there's been any work using some kind of different type of transformer, like a linear transformer, or some other kind of different kind of approach?
Yes. So there are several solutions that they try to solve this issue. For example, VIT has quadratic complex dependence. There is linformer that has linear complexity, linear dependence. Swin still has quadratic complexity, but from lower value. And there is another solution, perceiver, that in general doesn't depend on network resolution. So only the first block depends on network resolution. So I think this is just my opinion. This is better, so it doesn't depend on network resolution at all. So in this case, we can try to use it for multimodal tasks. We can try to use different images with different resolutions. We can use video, many frames, and text, and so on. And it will not depend on network resolution at all. So I think at least much more work I saw which are based on perceiver.
Thank you. Sasha, are you back with us?
Yeah, hopefully I'm back. Can you hear me now?
Yeah,
Great.
Okay. Thank you. Sorry about that. So yeah, super interesting talk. Thank you, Alexey. I also had a question about relating different architectures for different tasks. So perceiver is supposed to work for many different types of inputs. But in my experience, it doesn't work as well for dense prediction tasks as like the dense prediction transformer. There's like a huge performance gap. So I wonder, to what extent do you think that we should have like task agnostic architectures, or do we need like a different architecture for every task? And if we have like one big architecture, should we be solving things with just lots and lots of data?
Yes, that's a great question. So I think, and it's my opinion, that finally we need to use some one neural network for all, for the most computer vision tasks. And VIT is a great thing in this way, because it uses attention, and attention helps a lot to divide signals between different tasks if it's not if communication is not necessary, or it can allow to use information from different tasks. So for example, there were many papers, many works, and they tried to train one network with closely related tasks. For example, object detection and instant segmentation. And they got results that if you train one network with both tasks, then we can get high final accuracy for both tasks. And if you add another one task or some intermediate results, for example, if you add information from depths, from semantic segmentation, from normals, and so on, then we can get better final accuracy. And I think that finally we will have something like perceiver, one network that can be trained by using different tasks. In one network can be trained for different tasks and to solve different tasks simultaneously. I think different tasks will bring some new information that can help another one task. So I think so. So we need to use one unified neural network with attention.
So I guess to follow up, does that mean that you are on board with the foundation models approach? I don't know if you saw that like big paper from Stanford with like 10,000 authors that basically said like we should have one big, maybe BERT style model, but for vision that gets fine-tuned on different tasks.
Yes. So why GPT-3 is possible? Because we can scale up. We can scale up transformers very well, much better than recurrent neural networks. And the second thing is because we can collect very large data sets. So for GPT, we can just use Wiki or something else. For computer vision, it's much more difficult. We cannot collect very large object detection data set, or even semantic segmentation data set, but we can collect automatically very large depth estimation data set. as I said, we can collect it automatically, and we can use very large VIT. We can train it on depth, and this network will predict depth extremely great. So we can scale up it very well. And in this case, I assume that these depths, generated predicted depths, can help a lot for other computer vision tasks. So if we pre-train such very large neural network on depth or on some other computer vision task, then we can use these pre-trained weights to train other computer vision tasks to create something like GPT-3 for video. And at the same time, we can pre-train this neural network on depth, and then we can train it, fine-tune to predict labels, to do predictions for many computer vision tasks simultaneously, like detection, segmentation, and so on. So I think, yes, finally there will be such multimodal, very large computer vision model like GPT.
I think you are right that like GPT works because you have this big, you can get enormous data sets, and language modeling is a really good pretext task for language. In some sense, it's kind of like autoencoding for language, but it works really well because a lot of language seems to be related to that. In vision, I haven't personally seen one task that is so close to just like the base task for all of vision where you can easily fine tune. Maybe depth would be that if we scale up, but do you think that would be depth, or is it autoencoding, or do we know that task yet? I'm curious about that.
Yes, I also don't know definitely what exactly they will be, but I think so. At least there are at least two ways. The first way is try to train very large VIT on depths that can be collected automatically, and the second way, try to train VIT in BERT style, like in bait model and with masked tokens. And in this case, we can just use raw images without labels and try just to train model to in pain masked tokens. And in this case, we can collect a lot of images, unlabeled images, and pre-train on them.
Awesome. And I see that we have a couple of questions from chat. So I'll start with maybe chronological order. So one from Sergey asks, actually, Sergey, did you want to ask that, or should I just repeat the question? I'll repeat it for now. What do you think about hybrid architectures of CNN and transformers? For example, botnet from bottleneck transformers for visual recognition.
Yes, I also think that this is great. And currently, as I showed previously, Levit is a hybrid model. And as I saw for GPT, there is hybrid model that consists of ResNet and VIT, and it seems it's better for fine-grained details. And also QuadNet, as I remember, currently this is state of the art for ImageNet, and also this is hybrid model with convolutions and transformers. So I think, yes, currently hybrid models are the best, at least for ImageNet and some other tasks.
And then we have a question from John Poo, who says he runs YOLOv4 on an edge device powered by the Intel neural compute stick. And do you see any vision transformers being able to run on a small edge device, for example, this neural compute stick?
I did not try to. I did not spend a lot of time to try to run VIT models or some Levit or SIT models on Mirrored X on Intel stick. So I think it should be slightly changed. So yes, we need to use something like Levit or even improved Levit. So currently I'm trying to improve VIT, to run it on embedded devices and to run it with high resolution. But it's in progress, so I don't have a solution currently. And currently, I still prefer to use convolutional networks for low-level devices like NPU Mirrored X or Jetson. So, but I think in 1 year there will be some great VIT models for for NPU and low-level devices.
And this is cool because this is like one of the questions that I also wanted to ask.
Mm-hmm.
Often I see like maybe you train some big fancy model at one point using your enormous data set. And then when you want to deploy the model, maybe you have a smaller one that you distill the big model into the smaller one. Is this like a workflow that you see being a common thing with transformers? Maybe like you train a big transformer and then distill into a smaller common thing to deploy on edge devices? Or do you think that there will be just one model that you use everywhere?
I think so, yes, maybe so distillation and pseudo labels, it will help a lot. So currently, yes, this is very great area, and we use such approach. So for example, we're trying to train very large neural networks that is based on VIT. We try to generate pseudo labels on unlabeled data sets, and then we train our small models on this data set. But it helps a lot when we have a very huge gap. For example, if we train very large VIT, do pseudo labels, and then train on these pseudo labels very small model. In this case, it helps very well. It's great. So yes, this is a way. But if this gap is very small, for example, we train very large model and generate pseudo labels, but we then train on this unlabeled data set just medium model, then it doesn't help a lot. So I think, yes, it can be used just for distillation, for generated pseudo labels, soft labels, and so on. So we use it, and it helps.
And then there's oh, Martin, were you going to say something? I saw your.
Yeah, if you don't mind, Sasha, I was just going to ask you, so to go, just to concentrate on the convolutional neural network-based approaches like YOLOv4. Are you able, Alexey, to compare with anchor-free based methods? Because in my experience with the anchor-based methods, it can be quite sensitive to the anchor box configuration, and it's kind of annoying sometimes. How do we compare with anchor-free methods?
Yes, this is great questions. So in general, anchor-based methods more accurate with approximately the same speed. So it's preferably, but it's preferably only if we can generate these anchors. So for example, if we will train and use it on the same domain, but if we will train on some domain but use on another domain, we will have some different anchors. Anchors just are default sizes of objects at different scales. So in this case, anchor-based will work not very well. And there's another way. I saw some papers where they used anchors of wrong, so they generated wrong anchors, and it seems that generate correct answers is not very simple task, because we not only need to generate anchors, but also we need to assign these anchors to different output layers for corresponding sizes. So in this case, anchor-free detectors much easier to use, and for real life tasks, they can use it very easy. They don't need to generate these anchors to assign them, and they can get quite good accuracy. While if you use anchor-based detector, we need to spend a lot of time to generate and assign these anchors correctly. It's not very easy. So in this case, currently we use anchor-based. So YOLOv4 is anchor-based, and it works well. It is the best in terms of speed and accuracy for both data sets, COCO and Waymo, and many other data sets. But we need to spend some time to feed these anchors for these data sets.
Thank you.
And then also, I guess you mentioned generalization being a problem. Do you see a big difference in the convolutional versus the transformer-based architectures, and how will they generalize to sort of unseen images from either different data sets or real-world application?
I don't have quite fair comparison for these two networks, convolutional and transformer-based, but I saw, as I remember, a clip has very high zero-shot accuracy, on ImageNet. They trained it on some text and images, and then tested it on some unseen data set like stylized ImageNet or ImageNet adversarial and so on. And it seems that it shows very, very good accuracy. And also there was another one paper where they tested VIT and convolutional networks on stylized ImageNet. And it seems that VIT pay attention more on shape, while convolutional neural network pay attention more on textures. And it seems that human brain pay more attention on shapes. And it seems that in this case, VIT more are closer to human brain, just slightly. I'm not sure that this is great, this is better, but it seems that VIT generalize better. There is not quite fair comparison, but just my assumption that VIT can generalize it better.
I think that probably mirrors my experience too. Another question I had is, do you think that, you mentioned that transformers need generally larger data sets because they have maybe some inductive bias built into the network. And so you have to learn these biases. What role, if any, do you think that simulation has to play in generating data for these networks? Because if you simulate the data, then you can sort of generate any number of augmented views you want and try to learn these biases. So I guess, what role does learning the biases have versus building into the architecture? And then if you need to generate data for this, should you use simulation or do you need real data?
Yes, so I think that if neural network is shift invariance by design, then it should not be learned for this shift invariance, and it should not spend capacity of neural network for this shift invariance. While, for example, for VIT, it should spend some part of their capacity to learn this shift invariance. So it reduces, I assume that it reduces capacity of the network. So it's not very, very great. And it spend capacity, it needs longer training, it needs larger data set, and so on. So in this case, I think there should be something like hybrid model. So one part try to solve this shift invariant issue, and another part try to use these VIT advantages. So we need to somehow combine these advantages of convolutional network and VIT, like in QuadNet, Leavitt, and so on. So I think so. And very interesting thing. So I thought about two neural networks, scaled YOLOv4 and DPT, and it's very interesting that scaled YOLOv4 trained just on Coco training dataset. We did not use any pre-trained weights or any external dataset. So we did not use even pre-trained weights on ImageNet. So it's trained from scratch, and it is the best in terms of speed and accuracy. And it's very accurate. So it seems that it doesn't require any pre-trained weights or any good initialization or something else. It can be trained. While VIT mandatory should be trained, must be trained on ImageNet or ImageNet 21K, or even maybe in BERT style pre-training with masked tokens, or maybe on GFT or very large data sets like these 300 millions or 3 billion images. And it seems it will be difficult to use for end users, so they don't have such private data sets to pre-train such neural networks. While scaled YOLOv4, you can change the network and train it from scratch and get very high accuracy. So I think it's better to combine convolutional and VIT to make hybrid model that will not have such shift invariance problem.
Cool, thank you. And then one last quick question. I know we're up at the end of the time. Maybe you know the answer. One of your slides showed the Intel Ponte chip. Do you know how powerful this is compared to a TPU v4 or the Dojo chip?
Are you about Intel GPU? Or?
Yeah, I think so.
No, I don't have any information about this. Sorry. It's very interesting for me to.
We'll just have to wait and see.
Thanks, guys. I think we should stop there. Thanks so much, Alexey, for the fantastic talk, and Sasha for a really interesting discussion. Just a couple of points to make. I said that Evolution AI are the sponsors of the meetup. We are hiring currently for machine learning engineers, so please do check out the job on evolution.ai, or just email me. Just reply to one of the meetup messages if you want to know more details. Also, just, you know, this is our community, so if you have any requests for speakers, or if you want to moderate a discussion, or if you want to just get involved in any way, then please do let me know. Again, just reply to one of the meetup messages. Also, this talk is recorded like all of the talks, so please subscribe to the YouTube channel, which is London Machine Learning on YouTube. You can just Google London Machine Learning YouTube. And if you want to connect to me on Twitter, I'm at Martin Goodson. Thanks again to Alexey and Sasha. Really appreciate it. Thanks to everyone for coming along, and see you next time. Bye bye.
Thank you, Sasha, Martin. Goodbye.